Right. Today our emphasis is mainly to understand limiting and excess reagent. Limiting and excess reagent. Okay. Now, in simple terms, it is whichever reactant which gets completely consumed and it goes to the completion of the reaction is called limiting reagent. Okay.
Yes, sir.
So let me put that as a definition. Reactant which is completely consumed when reaction goes to completion, right, is called limiting reagent. For example, if you have A moles plus B moles is giving out C plus D moles here. Okay. Initially, I have Na number of moles and Nb number of moles. This is initial value. Correct? So, next thing what you need to check out is stoichiometric amount. Stoichiometric amount means how many moles with respect to the stoichiometric coefficient we have. Is this point clear?
So,
The amount with respect to the stoichiometric coefficient. Next, B moles, if you compare, it is number of moles of B divided by B.
hmm.
Now here is what we check out, that if, now we check this condition, if Na by A moles is less than Nb by B moles, then capital A, this is the reactant, is limiting reagent, LR. Okay. If Na by A is greater than Nb by B, then
Capital B.
B is LR, limiting reagent. Okay. That's how we check it out. There she makes sense, beta.
So,
Right. Let me back you up with this. I mean, if both of them are equal, then the reaction is completed. Both, no reactants will be left over. I'll put that condition also. When
sir.
these two are equal, then no A or B is left. It's not left anymore. Okay.
If you,
Now notice this example. Sorry.
sir.
One second. Is it visible now?
Yes, sir. Sir, I have a question.
One second. Let me give you one question which is related to limiting reagent, how it can be framed. Check. Imagine we have 28 grams of lithium is okay mixed with 48 grams of O2 to react okay according to the following reaction. According to the following reaction. Got it. That is 4 moles of lithium plus O2 will give you Li2O of 2 moles. Okay. If this is what has been given. So for limiting reagent cases, you need to have a balanced equation of the reactants. Got it? So without knowing the correct information of the reactants and products, we will not be able to guess. So here you take number of moles, which is 28 divided by 7, 7 being the atomic mass of lithium, and here it is 48 divided by 32. Okay, this is coming as 4, this is coming as 1.2. Hmm? And what is the ratio here? Stoichiometric ratio, that is 4 divided by 4 here, 1.5 divided by 1 here. So you are getting this value is greater, oxygen value is greater. Okay, beta? So which means that is the limiting reagent. Hence, we know that this is the, in this case, this is the limiting reagent. Hmm? Now, one thing you got to understand, Devarshi, is that limiting reagent is the one which will get completely consumed into product. So there will not be anything left once the limiting reagent is done. I mean, the reactant will not be left if it is a limiting reagent. Okay. And the reaction will also cease after that. No reaction will happen. So, which means the amount of product formed will always depend upon how much amount of reactant you have. Okay. Right. So, therefore, I can say that here we have 1 mole, here we have 1.5 moles. I mean, ratio wise, this is 1 mole is to 1.5 moles ratio. Okay. Hence, the product formation now you need to always check out with the initial moles how much you have to. So you can see every 4 moles are giving 2 moles. So if there is 4 moles, how many moles I'm expecting of lithium? 2 moles. So therefore, we can say number of moles of Li2O will be equal to 2 moles. That will be 2 moles. Okay. Make sense? So therefore, what is the mass of Li2O? That will be equal to 2 moles multiplied by 30. Molar mass is 30, which makes it 60 grams. All good? If in case I asked you, how much is the excess reagent left over? Amount of reactant left. Amount of reactant left will be equal to how much? Check. See, out of 60 grams here, I mean, you are getting 2 moles as a product. So you have to check out between these two ratios now. For every 2 moles, I'm expecting 1 mole is required. Correct? 2 moles, 1 mole is required. But how much moles extra I have? 0.5 moles extra I have. Okay. So therefore, amount of left will be 0.5 moles of O2. This is the leftover amount, which means weight of O2 will be equal to 0.5 into 32, which is 16 grams. So this is that extra amount which it has. Clear, beta? Right. Now, what if you have multiple reagents, multiple reactants? Check out the other example. Suppose I have a reaction where I have 5A plus 6B plus 7D plus 8F is giving, okay, 4G plus 2H plus 10Z, like this. Okay. Now my question is, if 5 moles each of the reactant, 5 moles each of reactants are taken, then find the sum of, find the sum of number of moles of B, G, and Z. Now this is how the question has been framed. Okay. In such case, how do we proceed? See, we know that these are the reactants which we have. First, write down all the number of moles initially. Initially, you have 5, 5, 5, and 5. Ratio, stoichiometric ratio, if you notice, it is 5 by 5, 5 by 6, 5 by 7, 5 by 8, which is clear that this is the limiting reagent we have. Make sense? Based on that limiting reagent, how much will be the product formation? Check it out now. Because every 8 moles is offering 4 moles of G and 10 moles of Z. Since I didn't ask any question about H, don't calculate about that. Okay. So for every 8 moles, if I get 4 moles, for 5 moles, how many I can get? So 5 cross 4 by 8. These are the number of moles of G, isn't it? Likewise, if you notice, for 8 moles, 10 moles of Z is forming. So this will be 5 into 10 by 8, which is number of moles of Z. Okay. Now you can use this information for identifying anything left over also. Check out. For 8 moles, 6 moles are required. But for 5 moles, how much is required? I'm writing it as minus. So it will be 6 into 5 divided by 8. This much is being used, isn't it? So number of moles of B, which is left, will be equal to 5 by 6 minus 30 by 8. So now I need to make out the sum. So number of moles of B plus number of moles of G plus number of moles of Z. Okay. So that will be equal to, here the 6 and 8, if you notice, the if you carry out the LCM here, so what do I get? Okay, 24. So it will be 6 fours. So this will be 20 minus 1 second, how much you get? Sorry, something, I made it wrong. 8 moles require 30 by 5. Sorry, this is not 5 by 6, this is only 5. Yeah, okay, because this is 5 moles I took, right, initially. So 5 moles I took. So how much we have here, beta? So 10 by 8 we have, correct? So 10 by 8 moles plus 20 by 8 moles plus 50 by 8 moles. This is what I'm talking about. Clear? So how much we have? 80 by 8. So total 10 moles. All good? This is a very easy one, but very tricky one as well. Okay. All right. Next. The other type of question, how it is framed, is like this. See here. 15 liters of nitrogen reacts with 30 liters of H2 to form ammonia. Find the final volume of the gases after the reaction. Okay, you know that number of moles ratio as well as number of volume ratio would always remain same. So you could always use this liter terminology same for moles also, right? So therefore you can see N2 gas plus 3H2 gas is giving 2NH3 gas. So this is the typical reaction of formation of ammonia. Here you see this as 15 liters, 30 liters was initially provided. So now you would notice that for every 1 mole, I would require 3 moles. So 15 moles require 45 moles. How much it is left? 30 is only given. So which is limiting reagent here? H2. Correct? Since this is limiting reagent, the product formation will always be desired, calculated on the basis of H2. So check out, every 3 moles is giving 2 moles. So 30 will give you how much? So 30 will give you 30 into 2 divided by 3. So which is 20 liters of NH3 formed. This much liters of NH3 formed. Okay, correct. And now do the reverse calculation, because for every 2 moles, 3 moles, or rather I could say here only we learned that for every 15 moles, how much was required here? 45 was required, but only 30 was left, which means this is the excess reagent, isn't it? Since this is excess reagent, check out how much is left over. For every 3 moles, 1 mole is required. So for 30 moles, how much it is required? 10 moles is required. So 10 liters is the used ones. So how much is left over? 5 liters is the leftover part. So therefore, total volume of gases, total volume of gases will be equal to 25 liters. Okay. 25 liters is the volume of the gases. Okay. What if I ask you, Yoshi, what if I ask you, what is the molecular weight, average molecular weight of mixture of gases? Mixture of gases. This is an add-on question. Okay. In such case, what we do, beta, you know the number of moles now, right? Because volume and mole ratio is very similar. So you calculate something called mole fraction. Mole fraction of N2 and mole fraction of NH3. So mole fraction is 5 divided by total number of moles. Here it is 25 divided by total number of moles. All good? So now you would use this logic to figure out how much will be the average molar mass. So molecular weight average will be equal to mole fraction of N2 into molecular weight of N2 plus mole fraction of NH3 into molecular weight of NH3. So it is 5 by 30 multiplied by 28 plus 25 by 30 multiplied by 17. Clear?
Yes, sir.
Right. So if I take 5 common here, so 5 by 30 can come out to be common here. So we will get this as 28 plus 17 fives, isn't it? So how much we have? 85. Hmm? So plus 85, isn't it? So how much we are getting? 113 into 5 divided by 30. Is that
Yes.
okay? So we have this as 130. 113, 1 second, 113 into 5, that divided by 3. So that is coming as 18.83.
Point.
18.83 as the molar. Ever see clear it out?
Yes, sir.
Please do check. If you have any problem, let me know. that okay?
Yes.
Right. See the next question. What if I add the same question with a slight twist here, beta? Same question again, but this time with a slight twist. The twist here is find the volume of the gases. Find find the volume of the gases if if percentage yield is, you know, 50 percentage. What if there is only 50 percentage yield? Okay. In such case, what would happen? Now you will do the usual tactic, usual thing what you have done it here. Okay. So this is what we have done. Correct. Now, in this, what you would see the next here is, since we have 20 liters of ammonia here, this is the theoretical value, isn't it? This is the
Critical value.
theoretical value. So, but practically how much we got? 50% of it, isn't it? So, since we got only 50% of it, I'll write down. So, this will be percentage yield is equal to 50 by 100 multiplied by 20, which is 10 liters. So, actually, we got only 10 liters. Hmm? But to maintain, to get the 10 liters, is it necessary that H2 and N2 both will be consumed? Not necessary. Both will be left over. Now check out how much is left over in that case. See, now you have to read it with respect to the actual amount. So for 2 volume, I require 3 volume, right? For 10 volume to prepare, how much would I require here? So subtract that. So 30, okay, sorry, 3 into 10 divided by 2. This much is the required amount. This is the used amount. Similarly, for 2 moles, 1 mole is required. So for 10 moles, how much is required? Minus 10 by 2 moles is required. Now subtract that. So how many we have? 10 liters is the leftover. This is used one. So this is the leftover. And here also out of 30 liters now, I am consuming how many? 15 liters. So how much is leftover? 15 liters is leftover. And how much is the volume that has formed? 10 liters. So therefore, total volume present will be equal to 35 liters. Is that okay? Done? Right. So this is about how to figure out the limiting reagent as well as the excess reagent. Okay, beta? The next term that will be usually asked is degree of dissociation. And this is something which you need to learn very strongly. Reason being, the concept is used in multiple topics: chemical equilibrium, ionic equilibrium, electrochemistry, kinetics, everywhere. So the concept is important. So check out what is degree of dissociation. So we'll start with the idea what is dissociation in the first place. Okay. Okay. For a chemical reaction, if let's say A reactant is providing n number of moles of B, where n is greater than 1, then A undergoes dissociation. We say A is undergoing or undergoes dissociation. This
Sir,
is what logically it means. Okay. Let me show you some examples. Suppose I have N2O4. On heating, it is becoming 2NO2. We say N2O4 got dissociated. I have PCl5. On heating, it has become PCl3 plus Cl2. We say it got dissociated. CaCO3, on heating, we get CaO solid plus CO2 gas. Should we call this as dissociation? Usually we should not call this as dissociation, because dissociation is always checked with respect to one type of phase. Here these two are solid phase, but this is gaseous phase. In such case, we do not apply the logic of dissociation. The phase of the molecule should be same. Got it? So phase wise, if you notice that 1 mole is giving 1 mole only, no? So in that case, it is not dissociation. It is decomposition, but it is not dissociation.
Sir, I have
That
one
logic
question.
clear?
Yes,
You're saying something?
sir, I have a question.
Yeah.
Sir, why does n need to be greater than 1?
Why n need to be greater than 1? Okay. Dissociation means from a molecule, you are trying to break it into multiple fragments. Okay. So imagine I took A as 1 mole. Stoichiometrically, nothing is written means I have 1. So after dissociation, it should be more than 1, right? That is what I meant. N is greater than 1. Okay.
Okay, sir.
Hmm. So whenever n is greater than 1, we say it is dissociation. What if n is less than 1? We call it as association. Okay. So that also we will learn it. But here in this topic, dissociation is more priority. Association, we have a separate chapter altogether. Okay. Hmm. So like this, any reaction, for example, if I take ammonia and it is giving N2 plus H2. So this is also dissociation. Okay. Number of moles of a particular phase should be increasing. Okay. Hmm. So how do we figure out, you know, dissociation, related parameters? The first parameter, what you're looking at, is degree of dissociation, where it is defined as alpha, and by definition it is simple: amount of, okay, uh, reactant reactant lost, how much it is lost, divided by amount of reactant initial. So initially how much amount it has. Okay, that's what you need to check it out. Initially how much amount it is and how much amount is lost. Sorry. So let me feed you more logically. Suppose if I have a reactant A is giving 4 moles of B. Let's say we'll start with simple example. Okay. I said that initially I took 2 moles of A. Okay. And after some time T, correct? I said that zero point 0.5 moles got consumed. Moles consumed. Correct. In that case, how much will be the alpha value? Alpha value is 0.5 divided by 2. Done. The amount consumed by 2. Okay. Then what is the amount left of A now? Because this is a consumed volume. So after time T, you will notice that 2 minus 0.5. This is the left amount of A. And what is the amount of B formed? That you will check out with respect to how much is consumed, right? But everything formation will be on the basis of stoichiometric ratio. So 1 mole is responsible for giving 4 moles. So zero point 0.5 will be responsible for giving how many moles? 2 moles. So basically we have 1.5 moles of A left over and 2 moles of B form. Does this example make clearer?
Yes, sir.
Right. Now let me put this in more generic format. Okay, that means as a formula. Hmm? So imagine a reactant A is giving n moles of B. Okay, so initially at time t equal to 0, number of moles of A, and this is 0. After time t, some x moles have been lost out of A, so n x moles of B must be formed, right beta? So based on this, can I say that the alpha value here will be x by A,
Yes,
x
sir.
by A, okay? And now notice how I can relate alpha in terms of various terms in this case, okay? Here, one second. Hmm. So the first term we will be learning out here is, hmm, when it comes to initial number of moles, initially I have only A moles here. This A moles can be related with its volume as well as its density, correct? Now let's say, if at all I would say that initially, 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 A moles relates to some V initial volume. And you know that volume of a gas will be, yeah, volume of gas will be inversely proportional to its density of the gas. This is initial, correct? So remember, Vi is initial volume, initial volume, okay? Sit here. Sit
No, I don't forget.
here. Relax.
Watch something. I'm gonna watch something.
Second.
Later.
Sorry, check out. So initially we have this volume. So Di represents initial density. So that is about initial density. Now after time t, what are the total number of moles beta? It is A minus x plus nx, isn't it? These are the total number of moles. So if it is for these many moles here, clear? Just a second. In such case, see, no talk.
Anna. That's Anna. That's Anna.
Shit.
Like daddy.
Second.
What? I feel forget.
Sir, your microphone is muted.
see, can I say that A initially is inversely proportional to density and final number of moles are inversely proportional to its density? In such case, I can write this as A divided by A minus X plus N alpha is equal to D final by D initial. Correct? D final by D initial. Okay?
Yes, sir.
All good? Right. Now, what exactly is X beta? X is nothing but A alpha. So you know
Yes,
that X is equal to A alpha. Let me put that value here. A divided by A minus A alpha plus how many we have? Nx. Sorry, this is not alpha. This is Nx here. Nx. So N into A alpha. Okay. Second. Right. So that is A minus A alpha plus N alpha. That is equal to D final by D initial. So which clearly suggests that AA will get cancelled. I will have this as 1 minus alpha plus N alpha divided by 1 is equal to D initial by D final. Does that make sense?
yes, sir.
Right. In chemistry, there is one convention we follow. Final, which is the mixture, is always taken as small d. Initial density is always taken as capital D. It is like a norm which we will follow. Right. So if I put that values here, so this will be equal to here. This will be equal to capital D by small d. Hence, now if I write this value here, 1 plus alpha into n minus 1 is equal to capital D by small d. So therefore, alpha into n minus 1 is equal to capital D minus small d by small d, which is equal to alpha is equal to d minus d divided by n minus 1 into d. So this is the formula that we can directly use to figure out what is the degree of dissociation. Got it?
Yes, sir.
Right. So I'll give you a second. I'll give you 20 minutes, seconds. Please check this through if you have understood that or not. Now see how this formula can be further changed into multiple things. See, we know that using using ideal gas equation, which is Pm is equal to dRT, I can say that density of any gas is directly proportional to molar mass of the gas, correct? So here I have a small density, which means it is of mixture, correct? So mixture will be equal to proportional to molecular weight of the mixture, and initial density will be proportional to capital D, which is initial density, is proportional to initial molar mass, correct? So instead of the density term, I can always use this term as well. So therefore, alpha can be written as molar mass initial minus molar mass of the mixture divided by n minus 1 into molar mass of the mixture. Now, molar mass can also be written as 2 times of vapor density, correct? Vapor density of the initial amount minus vapor density of the mixture divided by n minus 1 into vapor density of the mixture. This is another way of writing it, correct? And how we started is from this one, capital D minus small d by n minus 1 into d, correct? So these three are the formulas which are related to one another. So it can be asked in so many different ways. Okay. So sometimes the data would be of molecular molar mass, sometimes it will be of density, sometimes it will be of vapor densities. Okay. In any case, we should know how to use that. Hmm? Now notice this example. Okay. For a reaction, 2 moles of ammonia gas is giving N2 gas plus 3 H2 gas. Okay. Calculate alpha if molar mass of the mixture is given as 13.6 gram per mole. So pretty easy in that case. Which one will you use this formula? So therefore, alpha is equal to initial molar mass. Initially, what you have? You have only ammonia. Ammonia's molar mass is 17 minus 13.6 divided by N. Now, how do we define N? Check this, beta. N is with respect to 1 mole of the reactant. Okay. So you notice this one thing. For every 2 moles stoichiometrically, I would be gaining 4 moles in the product, correct? But if I take 1 mole, how many moles I should gain in the product? 2 moles. I mean, how many moles I should get? 2 moles. Okay. That N value is how many products you are getting, correct? So therefore, how many products you are getting in terms of moles? 2 moles. So 2 minus 1 into 13.6. Is that making sense? Clear?
Yes, sir.
So this value comes out to be 0.25. So one thing you notice that alpha value will be somewhere between 0 to 1. If the question is asked what is the percentage dissociation? Percentage dissociation is how much? 25%. Done? Just into 100 is the percentage dissociation. Now the reverse can also be asked. That is, if the uh, percentage dissociation is already given, using that case, how do we calculate the molar mass of the mixture? Correct? Or calculating that, we can find out what is the density of the mixture. Correct? These kind of cases can also be asked. So check out this example. Okay. 20% of N2O4 is dissociated. 20% of N2O4 is dissociated. Clear? On heating. Find the vapor density of the mixture. Find the vapor density of the mixture. Okay. First, you know that N2O4 will dissociate into 2 moles of NO2. Correct? You can write on this one like this. Okay. So you notice that for every 1 mole I take, I will get 2 moles of NO2. What will be the initial molar mass? Molar mass initially is of only N2O4, which is 92. That is initial molar mass. Which means what will be the vapor density initial? It will be 92 by 2, which is how much? 46. Correct? So we have to use this value now. That is 1 plus alpha into n minus 1 is equal to capital D by small d. This is what we got ratio wise. Can I write this as molecular weight initial by molecular weight of mixture, or vapor density initial divided by vapor density mixture? Hence, vapor density initial is 46 divided by vapor density of the mixture. That is the x value which I need to figure out. And that is equal to 1 plus alpha. Alpha is how much given? 20%. So 0.2 into number of moles is 2 minus 1. Correct? So what you are getting? X is equal to 46 divided by 1.2. Is this point clear, beta? Right. So that's how you can calculate divided by 1.2. I'll give you exact value. That is coming out to be 38.3. This will be the vapor density. So any dissociation cases, if at all you come across, I think you should be able to figure out from this page. Now, the next type of reactions related to stoichiometry is sequential and parallel reactions. Sequential and parallel reactions. Instead of writing any theory, directly let me explain you through one question. Check out. If a question is given like this, how many grams of H2SO4 is obtained from 1320 grams of PBS as per reaction.
Sir,
Okay.
okay. Sir, what is PBS?
PBS, lead sulfide. Now check out what do we have. PBS, right, plus O2 is giving 2 PBO plus SO2. SO2. This is the sequence. This is the first reaction given, and 3 moles of SO2 consuming on reaction with HNO3 plus H2O is giving out 3 moles of H2SO4 plus 2 moles of NO. This is how the reaction, this is how it has been related. Okay. Now, if this is the case given, now you're supposed to relate this one with this one. So you need to find out what is the commonalities between those two reactions. The common one is what? SO2. So you got to take that, understand that carefully. Okay. Now, start with balancing in case if it is not balanced. But since the question is already given in a balanced form, now what you check out? You relate how many moles you have starting with number of moles. So let's say number of moles of PBS is A. So for A moles, how many moles of SO2 should be forming? 2A. So I can say number of moles of SO2 should be equal to 2A. Agreed? And now relate SO2 with H2SO4. See, for every 3 moles of H2SO4 is forming. So for 2A moles, how many moles of H2SO4 will be forming? So number of moles of H2SO4
2.
will be equal to 2A only. Correct? So therefore, can I say that number of moles of H2SO4 will be same as 2 times number of moles of PBS? That's how you will relate it. Okay. This kind of relation is called sequential reactions cases. So 2 times of number of moles of lead, which is molar mass, atomic mass divided by given mass divided by molar mass. Molar mass of PBS is 240. Okay. PB is 208. 208 plus 32. 240. So that calculation will bring out around 5.5 grams. 5.5 moles, sorry. 5.5 moles. So what will be the weight of H2SO4 in that case? So weight of H2SO4 will be equal to 505 into 98. I guess this makes sense.
Yes, sir.
Right.
Right. Let me take
Let
one
me take one
sequential reaction
sequential
as well.
reaction as well. Check out the parallel reaction. Parallel reaction cases. So parallel reaction is like, a reactant A is giving B plus C. At the same time, A is also giving C plus E, something like this. So it is not only depending on one reaction, there are two different reactions happening. Now, can I write like this? 2A is giving B plus 2C plus E. This is wrong. Okay. Because the amount with which the reaction is going here might be different here as well. Okay. So we can't simply add those reactions and write. Right. These type of reactions are called parallel reactions. So for example, I'll take one organic question here. Okay. See this question. Suppose I have a reaction where I'm treating this with this chlorine. Okay. I'm treating this with H2O and water. H2O and heat. Correct. So this is giving a product. And let me write down this as a reaction itself. So it is like, let me take. So one reaction that is happening is I am getting a double bond here plus I'm getting H2 here, HCl, HCl here. This is what is the product you're getting. Of course, ROH is coming out again. That means it is like a catalyst. It has no such role as such. But in the second reaction, there is actually a role. That is, ROH is making a reaction here where it is making a reaction like this as OR plus HCl. This is the reaction that is forming. Okay, beta? Now, how much amount of HCl is forming in both the cases will be different because we don't know how much percentage that has been reacted here and how much amount that has been reacted here. Okay. So if I tell you like this, if 40, if 100 grams of reactant reacts with ROH to form product A and B to form product A and B, then find the amount of A and B if mole if 20 percentage of reactant gets consumed by first reaction. Okay. If 20% is consumed by the first reaction, rest of the 80% is consumed by the second reaction. So let's see that here. So if at all I copy that again, let me put that here. See. So the first reaction is consumed by 20%. So the first, let us calculate number of moles. So number of moles include, okay. So how many moles we have? Let me just put that value here. So 60 plus 1 second. 60 plus C5. This is C5 means 11 plus 35.5. I'm writing the molar mass. Right. So 106.5. 106.5. So I'll do one thing just for our clarity. I'll put this as 106.5, making the calculations more easier. Okay. So imagine if at all I have 106 I mean I have total of 1 mole here. So 1 mole making a reaction with the first case. So here I have 1 mole. So out of that 1 mole, how much is the percentage that has been reacted? Only 0.2. 0.2. 20 percentage means 0.2 moles. So now use the stoichiometry here. That is how much is remaining? 0.8 is remaining. So that 0.8 must be reacting here. So you have to get the product based on this, So check out. First we have uh, 0.2 means 0.8 moles here. 0.8 moles means this is also forming 0.8 moles. So 0.8 moles of A, sorry, 0.2 moles of A and 0.8 moles of B. Correct. So I need to find out what is the amount of A, sorry, not B, amount of A if 20% of this is reacted. So amount of A is this much. So weight of A is how much? So weight of A is equal to, this is 1, 2, 3, 4, 5. 5 carbon. 5 carbon means we have 60 plus how many carbons we have now? C5 plus 10. So total 70. 70 molar mass multiplied by 0.2. So that is the weight of A. Correct. So which is how much weight of 14 grams. So that is the weight of A which has been formed. This kind of reactions are called parallel reactions. Okay. Yoshi, I guess this part is clear now.
Sir, I have a question.
Right.
It will parallel
Yes,
reaction will
please.
not happen if one of them is the limiting reagent.
If one of them is limiting reagent, then what happens in the parallel reactions? See, how much limiting amount is there? That much you have to consume. Correct? Because you have identified the limiting reagent. So based on that limiting reagent, you will consume that amount of the reactant in one equation where you have. Accordingly, you will get the product. Okay. The remaining amount which you have it of the reactant, that also you will check out in the next reaction, the leftover amount, and based on that, you will find out the product.
Sir, but aren't limiting reagents completely used in reaction, so there will be none left for the next one.
You're saying that limiting reagent itself is used in both the reactions. Instead of something else, limiting reagent is being used. Good question. See, if let me show. Imagine iron is reacting with iron is reacting with O2 to form Fe and Fe, sorry, FeO and Fe2O3 with excess of O2. Okay, it is with excess of O2. So if it is with excess of O2, we know that one reaction is Fe plus O2 is giving FeO. This is one reaction. Second reaction is 2Fe plus 3 by 2 O2 is giving Fe2O3. That is the second reaction. Okay. Because because oxygen is in excess amount, iron is limiting here. Correct. Let's say I said 100 moles have been used here. Total 100 moles of iron is present total. So out of this 100 moles, some moles will be utilized here because it is limiting amount. Correct. This is still in excess. We are not worried about that. This is still in excess. Correct. Because this is limiting, it will totally consume here and here. Let's say I got A moles got consumed here. So I'm not worried about how much oxygen it is, but I know that A moles of FeO is formed. Here, let's say B moles got consumed. So I say that out of 100, B moles got consumed here. Correct. So how much it should form here? B by 2 moles should be formed here. Correct. But one thing is for sure, because if iron is limiting, if Fe is limiting, then A plus B have to be 100. This is what it should be. That is the advantage you will use. That's it. Does that make sense now?
Yes, sir.
Right. Next, the last part of this topic, correct, relates to the last part of this topic relates to uh, empirical and molecular formula. Empirical and molecular formula, which is usually been asked, and how they are related is been asked. For example, if I ask you what is the formula of glucose formula. Glucose is basically
H12.
C6H12O6, correct? This is the formula. So this formula is called as molecular formula, MF, molecular formula, correct? Empirical formula is the smallest ratio of these atoms in the molecule. So what it is, HCH2O. What will this become now? This is empirical formula. Okay, so this is smallest mole ratio of atoms. That is empirical formula. You see, that makes sense? Yeah.
Just want to watch.
So check it out. This is the empirical formula now. So how to figure out this and how to relate this empirical formula and molecular formula, and where exactly is the advantage we will get for this one. Okay. Let us do through one simple questions here. Got it? Wait, finish. So let me show you the uh, case here. Okay. The question usually asked is figure out the empirical formula as well as the molecular formula. Okay. Let me write down through an example here. An organic compound contains an organic compound that contains 49.3% of carbon. Contains 49.3 percentage of carbon, 6.84 percentage of hydrogen, with vapor density of 73. Vapor density of 73 given. Find empirical formula and molecular formula. This is a very typical question. Okay, standard JE question also, and standard NSO question as well. Okay. Now, how do we identify that? Check out. You know that the you can figure out by a table here. That is, you start with elements, representing elements. We have three elements here: carbon, hydrogen. Correct. The rest is of oxygen. Okay. Usually that will be given. The rest is of oxygen. Karke. In that case, now you check out what is the percentage weights that has been given. So it is given as 49.3 percentage. Hydrogen given is 6.84 percentage. The rest will be oxygen, which is 43.86 percentage. I'll get. Okay, beta.
Yes, sir.
So if the percentage weights are being given, now what you can do here is calculate number of atoms. So number of atoms can be calculated as 49.3 divided by atomic mass, which is 12. That divided by 6.84 divided by atomic mass, which is 1, and 43.86 divided by atomic mass, which is 16 for oxygen. All good?
Yes.
Correct. So using this, you will get certain ratio here. Got it? So this is coming out as 6.84. Correct? This would come pretty close to, right? This will this value will come very close to something like how much it is. 12
Four,
12 means somewhere around 4 point something. Okay.
4.2.
4.2. Let's put that. Okay. Now here, this one will be 14. I mean 16 goes close to
2.8 something.
2.8 something. Yeah. Now identify whichever is the lowest value and divide it by the numbers here. Okay. So now you will get the uh, closest ratio of atoms. So which is 4.2 divided by 2.8, 6.84 divided by 2.8, and 2.8 divided by 1. Okay. Is that okay?
Sir, why 2.8 divided by 1?
Sorry. I mean 2.8 divided by 2.8. I mean the value coming out is 1. Okay. So when I get this as 1 here, multiply this with 4 again. So 1 into 4 here, multiplied by 4 here, multiplied by 4 here. This value will come very close to 6. And this value will, sorry, not 4. I'll do one thing. Multiply that with 2. 2 is enough. Multiply that with 2 here. So this value will come very close to 5. And this value will come very close to, let me multiply 2, 2. This value will come very close to 3. This value will come very close to 5. And this value will come very close to 4. So what we have here is carbon 3, hydrogen 5, and oxygen 4. So this is the empirical formula. Empirical formula. While now notice what is the empirical mass. Just like molar mass, what is empirical mass? So how much we are getting? 36 plus 64 plus 5. Correct. So it is coming close to how much? 30,
105.
yeah, 105 grams. Correct. This is coming out 105 grams. And if you notice, the vapor density which is given is 73. So using vapor density, can I calculate molecular mass?
Yes, sir.
So molar mass is coming out to be close to, 73 multiplied by 2. That is a molar mass, isn't it? So that is how much here? 3 to the 6, 7 to the 146. Correct. One second. 146 is correct, but I think the ratio which I'm getting is not very close value here. This molar empirical mass should not come like this. Sorry, this is 2. Sorry. O2. This is O2, no, beta. This is not 4, this is 2. Yeah. So this is 32. So how much we are getting here? This is coming out as 73 only, no?
73, yes.
Hence, now you notice that the n factor is called the molar mass by empirical mass. Molar mass by empirical mass. And that value I'm getting it as 2. Therefore, sorry, molecular formula will be equal to C3H5O2 times of N, which is C6H10 and O4. So that's how the molecular formula will be calculated. Is that okay?
Yes, sir.
So I am sure you do understand this case, no? It's not that difficult either. Okay. The very standard one, simple one, which is usually asked in such cases. Let me give you one of them. You can try it out, correct? With respect to chlorine, okay? Please try this out. A moth repellent, a moth repellent has composition 49% carbon, 2.7% hydrogen, and 48.3% chlorine. Its molecular weight is 147. Find empirical formula and molecular formula. Clear? Right, but I'll give you 2 minutes. Please solve and let me know. Repeat, empirical formula is
C3H2Cl1.
H2Cl1. So which makes molecular formula as
C6H C6H4Cl2.
Cl2. Correct. Okay. This is usually a structure of dichlorobenzene. Correct, like this. Chlorine, chlorine, and benzene. Clear now? Right. So typically these kind of questions are being usually asked from this area now. It's the last area which you need to learn it. Correct? Uh, there is one very raw method of identifying the atomic masses. Correct? So that raw method, in fact, this is empirical only. That means there is no scientific proof for it. I mean, there is no, I'm sorry, a theoretical proof for it. Correct? It is based on a scientific experiments. Okay, so for identification of identification of identification of atomic mass identification of atomic mass the first method we will use is Dulong Petit method. It's called Dulong Petit method. Okay, it's specifically checked for solid elements. It is only checked for solid elements. Got it? It says that the atomic mass of metal or something which is solid into specific heat capacity which is normally given to you for such cases, which is usually measured in calories per gram. How much calories per gram per degree Celsius is been given. That product value is approximately equal to 6.4. I mean, the total is 6.4. Correct. If this value has been given for a particular metal, that is the way you can calculate the atomic mass. Okay, let me show you with an example. Got it?
I had a class at 6.
1 second.